I just put my slides in the chat, and so if people don't want to keep up with the talk at the speed I go, either ask me to slow down or have a look at the slides which are posted there on my webpage. So there was an abstract to the talk, and I basically wanted to point out that I'll talk about these things called fission spaces, and these have a long history that they actually appear in a paper of Birkhoff, and then we sort of proved that they were quasi-Hamiltonian in 2002, and there's been a story about how to extend that. So I wanted to give the precise references there. Okay, there's also a survey paper from 2017 which sort of talks about the philosophy of the basic question that we want to have a look at about how to sort of classify lax representations, the lax projects. And so there's more about different perspectives on that in this paper. It was published in Hitchin's birthday proceedings, so that's also on the archive. Okay, so I'd like to start with this like sort of global Lie theory picture. So from a very simple perspective, you can start with a Lie algebra, and you have this exponential map which gives you a map to the group. And so we have this like additive or Lie algebra picture, and then we have this Lie group side over here. So x goes to x of x. So for instance, you might just take, say, g to the GLNC, and that would capture most of the interesting things that happen here. Now, it's a very simple remark that rather than thinking of this abstractly as the exponential map for a Lie group, we can also think of it as the monogamy of this very simple connection on a punctured disk. So I can just put x as the residue of this, so basically a matrix of meromorphic one forms on a disk. And so I have a punctured disk where I can sort of look at the monogamy around there. Hello? Is there a quick question? And this will give you a different perspective on this same map. So basically the monogamy of a simple connection like this is just e to the 2 pi I times the residue. But having phrased it in that way, we then get a much more general perspective. We can just replace this matrix of rational one forms by an arbitrary matrix of rational one forms. So for instance, something like this. So here the AIJs are just arbitrary n by n matrices. And the basic fact is that there's a way to define invariants of these which generalize the monogamy. So there's a long story in the math papers of what is the monogamy and Stokes data of an arbitrary meromorphic connection on an algebraic curve. So you get lots of holomorphic maps that generalize this exponential map here. So the basic game that we want to play, so the point is basically that there's a natural Poisson structure on the additive side, on the space of rational connections, and this also extends to higher genus as well. And so we want to look at a good symplectic leaf of that, and I'll talk about what I mean by good later on, but there is a class of generic or sort of good symplectic leaves such that we know how to define a Poisson variety on the multiplicative side, which has the same dimension. So the basic aim of the talk is to sort of talk about the multiplicative picture, given that there's lots of standard or sort of different perspectives on the additive picture, in particular the standard R matrix way of constructing the Poisson structure over here will match up. So to be slightly more precise, so at the moment I just want to sketch the big picture before specializing on particular cases. So we would fix a symplectic leaf and then look at these up to isomorphism, so quotienting by sort of diagonal conjugation by the constant group. And it's possible to construct a symplectic or Poisson moduli space over here, and the corresponding sort of space of Stokes representations or Stokes local systems, the Betty moduli space in this situation having these higher order poles as well. And so there's a class of spaces such that you have these generalized exponential maps, the Riemann-Hilbert-Birkhoff maps from the additive picture to this multiplicative picture. Okay, so one could be slightly more precise. There's a way to factor this. There's you notice after a bit that people understand the definition of what a connection is, and there are connections on non-trivial vector bundles. So here we're basically looking at connections on the trivial vector bundle on an open part of a punctured Riemann sphere. And it's possible to understand how to extend the bundles across the punctures and cook up a precise moduli problem such that there's an algebraic moduli space, the Dirac moduli space of meromorphic connections, such that you have an algebraic inclusion from this additive moduli space into here, and then the Riemann-Hilbert-Birkhoff map can be souped up to give a complex analytic isomorphism between this Dirac moduli space and this sort of wild character variety or irregular Betty picture here. So you start to get a slightly more sophisticated picture like that. The fact that this can be, the injective map like this in the generic case was in a paper of Jimbo Miranoeno from 1981, and I pointed out in my advances in math paper in 2001 that it's possible to define a space by having non-trivial bundles such that you get an on-the-nose, bijective map here, explaining, what the complement of this large open patch is in terms of, connections on degree 0 vector bundles that may not necessarily be trivial. And so there's this dense open patch, something like the complement of the theta divisor, which is this additive moduli space M star here. Okay, now that's the main picture we want to have a look at, but let me just mention that there's a more like hardcore analytic picture as well if you incorporate a Hermitian metric. So the basic story says that it's possible to use the stability conditions for these connections to give the existence of solutions to these self-duality equations in dimension 2, the so-called Hitchin equations. So locally, they're just the maps through, for a harmonic metric, so maps from a small piece of the surface into the positive definite Hermitian matrices. So Hitchin had this beautiful picture where he looked at the case of a compact surface without any poles, and he related solutions of this to representations of the fundamental group. And it turns out that if you don't insist on looking at the finite energy solutions, it's possible to incorporate the poles and still get these complete hyperkähler metrics as well. So that there was a sequence of papers. I think the first paper in the non-compact case was the paper of Kono that used Bicard's analytic package to say that there were complete hyperkähler metrics in that case. His case was still the finite energy picture, the so-called the strictly parabolic tame Higgs bundles. And then there was a paper of Nakajima that says that there was still the metrics in the SL2 case with the tame poles as well. And then there was this paper with Bicard that proves that there were complete hyperkähler metrics, even in the case with arbitrary order poles, in particular when the case where the energy is infinite, that we do go beyond the instanton type picture that Hitchin was having a look at. I mean, if you have a look on the first page of Hitchin's paper, he says that there are no interesting solutions on R2. And then it turns out that there's a huge sort of bestiary of complete hyperkähler manifolds which occur. And part of the story with the diagrams I want to get to is to try to, navigate through the bestiary of examples which occur to try to classify the manifolds which occur. So the rest of this abstract story goes something like this, that there's a theorem of Sabah which says that the stability condition for the connections gives you the existence of a Wiles harmonic metric, and this generalizes the work of Corlett and Donaldson. And then you can also get the correspondence with these Higgs bundles as well. So this would be like basically the rational L operators that people think about in the integrable systems, maybe multiplied by dz. And so the point is, if I'm looking at connections, if I do a gauge transformation, you get this extra term like dg G inverse, and then you can take the autonomous limit of that to get to this Higgs or L operator picture where you're just acting by conjugation. So there's a stability condition for these, the meromorphic Higgs bundles, and that turns out to be also the condition for the existence of this harmonic metric as well. So there's this big picture of a hyperkähler moduli space of solutions of these Hitchins equations with irregular poles, and then this has these three natural algebraic structures as the space of Betty data, the Stokes and monogamy, or it has this different algebraic structure on the other side of Riemann-Hilbert as the modular space of meromorphic connections, and then it has this third perspective, which is actually this lambda deformation of the connection algebraic structure to give you the Higgs bundles, or if you like, the rational L operators which occur in the the lax pairs for lots of classical integrable systems. So I'll call this whole package a non-abelian Hodge space, extending the terminology of Simpson, who looks at the compact case and the case with tame poles as well. So the point is that these spaces have lots of the same properties in the wild picture as in the tame picture that Simpson looks at in his 1990 paper, and that was extended to the hyperkähler manifolds in his work of Kono and Nakajima. So the point is we would like to view these as some kind of generalization of Lie groups. They are the things on the multiplicative side which occur here. And it turns out if you look at simple examples, that often these additive spaces M star are isomorphic to Nakajima quiver varieties. And so the strategy is to try to use the quivers which occur to try to classify these spaces. And then it turns out it's possible to generalize the quivers to what we call diagrams, which works out for all of, which can be naturally defined for all of the cases on the Riemann sphere. So I want to focus on P1, mainly because we then have this natural sort of Lie algebra as well, which is somehow missing in this like pure math higher genus perspective that Hitchin had a look at. There's not this, natural open patch where you look at the bundle to be holomorphically trivial, but also because we get lots of interesting isomorphisms between these spaces. Is there a question? So someone has their microphone on, and I can hear you, but I can't translate from the Russian.
提出しない。自分でやってるだけ。
Okay, I'll ignore you.
なんかわからないのとかないの。
Is it possible for the people in charge to switch off everyone else's microphone?
I think we need all to mute their mics with the exception of Philip.
If possible, that might help.
問題を解く感覚を思い出すみたいな感じですか。
Is it Japanese or Russian? I don't know. So, anyway, so the basic plan, I want to talk about the techniques, the basic picture, how to construct these Betti spaces as algebraic Poisson varieties. So there's like a long story that we get this new class of algebraic Poisson varieties by extending what people did in terms of space of representation of the fundamental group to these Stokes representations, or Stokes the local systems. I want to start with there, and then I'll go back over to this M star picture and explain the link to quivers which occur if you look at certain examples, that M star is isomorphic on the nose to a Nakajima quiver variety in lots of cases. And then I want to go back over to the multiplicative picture and see how to read that quiver off on this side. And once you do that, you see that it actually works in general, even in the twisted case. So basically there's a twist which occurs in lots of examples, and somehow that sort of means that your M star is not isomorphic to a quiver variety. For instance, you'll get the the D2 ALF space if you just have two poles of order 2, which is sort of more multiplicative than a quiver variety would be. So there are still additive spaces which are interesting, but are not isomorphic to quivers as well. I wanted to mention the link with the physics. I'm not an expert, but I've read enough papers to be able to like repeat a number of the words that people say. So basically, I mean, if you look at these Seiberg and Witten papers in the 90s, they have a quite clear story, at least for certain examples, where they look at 4 dimensions n equals 2, and they compactify an R4 to get what is like the base of the meromorphic Hitchin system. And then they have a story where you compactify an R3 cross S1, and this gives the total space of one of these non-abelian Hodge spaces here. And then there's a story, so the story would be that the Coulomb branch compactified on R4 would be the base of the Hitchin system, if I understand correctly. The Coulomb branch compactified on R3 cross S1 would be the total space here. I'm not sure which algebraic structure people would prefer, but analytically it is this space here, I think. And then there's this story of taking the limit where the circle becomes a point and you get down to this 3-dimensional picture. And at least in certain examples, these are isomorphic to these spaces M star. And it would be interesting to try to work out a dictionary how much overlap there actually is. And I will focus on this kind of multiplicative story and not talk so much about the additive picture, except for the one which is related to quivers. But nonetheless, I think physicists are interested in that because it does predict a certain number of the mirrors which occur in this 3D mirror symmetry picture. There's a number of papers of Dan Shi which explain various aspects of this story. Okay, so let me sort of slow down and talk about, sort of parts of it in detail. So I want to focus on the Betty picture in simple examples, and I want to explain the simplest examples of these fission spaces which occur. So you have an annulus like this. So basically I've taken a sphere with 2 marked points. I've done the real oriented blow up there to get this annulus here. And then we want to draw this other circle and mark the boundaries with 2 groups G and H. So I have a vector space V and it's graded by some set I. So it breaks up into these pieces. I have an I graded vector space. I take G to be all of the automorphisms of V and H to be the graded automorphism. So H is like this block diagonal subgroup of G. And I put H near the outer boundary, actually where I would have the irregular pole, and G at the boundary in the middle. And then I'll choose the integer K, which is related to the order of the pole. And in the simplest untwisted case, I would just mark an even number of tangential punches. So I get this surface with these extra punches, the tangential punch. I'll call that sigma tilde. And I'll mark each of the tangential punches with a unipotent group, a Stokes group, which alternate between being U plus and U minus. So these, block unipotent groups where the block diagonal part would be like this group H. So then we look at a special type of flat connections or local systems on this. So we have a reduction to H in the boundary piece here. And so that's like you have a local system of rank, so it's locally isomorphic to V, but it's graded in this piece here. So the word fission is related to the fact that the structure group naturally gets broken from G to H. In the outer halo here, it's naturally graded by this set I into the same dimensional pieces as we had in our graded vector space in the start. And in the middle, we just have a G local system, and this has to be defined across these intervals between the tangential punches as well. And you put in the condition, the Stokes conditions, that if you sort of start in the halo and you go around one of these tangential punches, then the monogamy has to be in the corresponding Stokes group. And so you have a well-defined class of Stokes local systems which occur, and these turn out to classify certain connections. So I can just start out with a particular connection. I'm describing to you one way to get the Betty data of those. This is actually very close to Stokes's original picture, that the grading which occurs here is just a very sort of neat way to classify the formal connection. So once I pass to the formal punctured disk, you can do a lot more gauge transformations and all of the connections are actually graded. In general, they'll be graded by a twisted cover of the circle of directions. But in these examples to start off with, I'm just looking at the case where it's graded by some set I, which intrinsically turns out to be the exponential factors, but we'll get to that later on. So there's a grading which occurs near the boundary. And what Stokes was really doing was this multi-summation or Borel summation picture, where you actually have a natural way to glue your formal solutions near here to the actual solutions of the solution in the interior of the curve. And so that gives this Stokes gluing between these pieces. And at the end of the day, you can write down the axioms that they obey, and that will give you this definition of a Stokes local system, which I just described. I wrote a paper which describes all of this in great detail because it's kind of hard to read it in intrinsic language. So I wrote it down and put it on the internet. And so if people want to know the clean way to make all of these definitions actually in 3 different perspectives, you can have a look at this paper, Topology of the Stokes Phenomenon. But that's not my main focus. I mean, there are sort of videos on the internet which describe that as well. Today I want to sort of first of all go towards this quasi-Hamiltonian picture. So let's look at the moduli spaces of these Stokes local systems. So we can classify these. Let's just choose a base point on each of the boundary circles, and we could define this groupoid, the fundamental groupoid of this curve sigma tilde. So we're looking at all of the paths in here which have these base points on the boundary like this. We have this wild surface groupoid. And then we want to look at the space of Stokes representations of this. So the representations of the groupoid, what is the monogamy or the parallel transport which arises from this type of local systems. So we can just write that down explicitly. We get this subspace, the Stokes representations inside the space of all of the representations of the maps from pi into G. And if we choose particular paths, we can identify this explicitly with sort of G cross H multiplied by the product of all of these Stokes groups. So like the G here would be the connection matrix between the boundary, the H element would be the monogamy around the boundary, the H boundary here, and these will be the monogamy around these Stokes groups, something which goes like out and around and then back. The Stokes automorphisms. Hello?
Yeah, so I have a question. So this G, you said it corresponds to what? To the holonomy from B1 to B2, is it right?
So the G which is here would be the connection matrix between B1 and B2. If you know my early paper, this turned out to be these Doyster maps, which were related to this Ginsburg-Weinstein isomorphism. But just, it's possible to choose generators of pi, which give an isomorphism like that. You can do that in various different ways. The standard way would have the G part going between the base points, and then H and all the rest of these will be based at the H base points here, where you have this reduction of structure group. And so in particular, I can drag the Stokes groups to here within this graded local system. So, it has this concrete description of this, but abstractly, it's just the set of isomorphism classes of Stokes local systems, which are framed at these base points. So at the graded base points, I have a choice of a graded isomorphism between the fiber of the local system and a standard copy of a graded vector space, like at the top here. And here I just have an arbitrary isomorphism between the fiber of the local system and a fixed vector space V. So this will have a natural action of G cross H. So the theorem that can be proved is that this is naturally a quasi-Hamiltonian G cross H space. So this action we just described by changing the framings at the base points, and it has a moment map, a group values moment map, which gives the monogamy around the boundary. So it's a map to G cross H. So the component into G will be the monogamy around the boundary here, and the map into H will be the graded monogamy around the boundary there. So mu is just the value of the Stokes representation on these loops around each of the boundaries. So, I mean, this was proved in the generic case where H is a torus in 2002 for arbitrary reductive groups G, and then it was extended. This is the first case with block diagonal H, and then it was extended to the general untwisted case in 2011. And then there was this paper with Daisuke in 2015, which did the twisted case as well, which eventually I'll get to examples of at the end. But that's the basic picture. There's this new class of quasi-Hamiltonian spaces which occur if you allow these wild boundary conditions for connections. So I haven't defined what a quasi-Hamiltonian space is. I was hoping this would become a completely standard thing, but you should read the paper of Alexeyev, Malkin, and Meinrenken in 1998. They came up with this really nice language for how to construct these modular spaces by fusing together pieces. So the basic example would be, if you have a surface with one marked point on the boundary, then they proved that the representation variety, so without quotienting the framed moduli space, is a quasi-Hamiltonian G space with the action of G given by changing the framing as before, and the moment map being the monogamy around the boundary. So the picture we have here is an obvious sort of extension of that, where you have this reduction of structure group. I'll get to pictures later on where you're actually supposed to think of the H boundary as been like splayed or fissioned away, that it is actually breaking the group into these individual pieces. At least in the GLM picture, there's a quite clear picture that the boundary is actually fissioning or splaying. So the basic examples were these. So the moment map explicitly is just the product of these multiplicative commutators. And so a consequence of their results, I mean, this is actually the complexification. They looked at compact groups. I was interested in the case, if you transpose into sort of complex reductive groups, then you have these holomorphic symplectic structures, and eventually you can do it in an algebraic way and get lots of algebraic Poisson varieties. So the basic statement is that the straight quotient, looking at the set of closed orbits, or the GIT quotient, is a Poisson variety. So the quasi-Hamiltonian 2 form which occurs here gives you an algebraic Poisson structure. And the symplectic leaves are got by fixing the conjugacy classes of monogamy around the boundary. So I think basically these statements were known, but this gave a very clean way to get them by chopping up the surface into pieces. So a basic example would be the compact character variety. If you take the conjugacy class to be just the identity, the point then you just get the straight quotient, which lots of people have looked at. So the strategy was that you can fuse these simple pieces, that you don't need to work very hard to get the structure. You can just do it on simple pieces and have this fusion operation. So for instance, you can take this internally fused double, the quasi-Hamiltonian space attached to a one-hole torus. And then they have this fusion operation, which is basically the product of the spaces. You fuse all of these pieces together, and then you cap off to get the simplexical Poisson moduli space here. So you have this toolbox where you have the internally fused double, you have the double, which has these 2 points on the boundary, which comes from the annulus or this cylinder equivalently, which is a quasi-Hamiltonian G cross G space. And you have this fusion operation, this reduction, which corresponds to capping off, or you can also reduce at a conjugacy class as well. So all of the tame character varieties can be got very cleanly in this perspective. You just have G copies of this internally fused double fused together, and then M conjugacy classes CI. So the conjugacy classes are quasi-Hamiltonian spaces, with the inclusion being the moment map into the group. So it's a clean, sort of multiplicative version of the usual picture of a coadjoint orbit, having the moment map being the inclusion in the dual of Lie algebra. So this was their way to construct these tame character varieties, the Betty spaces that Simpson and others might speak about, at least after you complexify their compact group picture. But they had a very clean way to do that in a later paper in 2000. The original proofs did not work directly in the case of compact groups, but it's possible to adjust them such that they do. And I used this sort of complexified, holomorphic and algebraic perspective in my 2002 paper without carefully establishing that everything does actually work. But that was done in this sort of Dirac perspective paper with Burstein, by Alexeyev, Burstein, and Mein-Renken in 2007 or so. Okay, so the basic strategy is, if you look at connections which have irregular poles, then you get a much larger toolbox. In particular, you can add these untwisted fission spaces that we looked at just now. So now you've got this breaking of structure groups, so you can glue in lots of weird ways and get surfaces that have different groups in lots of different pieces. So I was interested in the particular class which occurs when you have an irregular connection on an affine algebraic curve, in which case you just have the group G in the interior and you have these descending boundaries. You might have to glue these fission spaces end to end in the case of multiple levels, but it's always got this large group in the middle. But there were these fission conjectures in this 2009 paper, which says that maybe you get hypercalometrics also in the case where you get all these different groups all over the place as well. And I don't know if there's really much progress on that, but I would perhaps like to advertise that, one would like to know whether there's lots more happening there. So there's particular pictures in that 2009 paper, which has, 3 different groups being included in a particular way. From this perspective, we clearly get a Poisson or a simplexic structure, and one would hope that these can be upgraded to hypercalometrics as well. So you got this general class of varieties which are called fission varieties by gluing all these pieces together. And amongst those, there's a special case which do occur in this sort of wild nonabelian Hodge picture, the wild character varieties. That can be extended to the twisted case also, with the gradings that are twisted at the boundary, but I'll get to that in a moment. So the particular motivation, I read this paper of Jimbo, Mira, and Ueno. I was trying to understand Dubrovin's work on Stokes data and the braiding of Stokes data which occurred there. And the best presentation of the general picture was this 1981 paper of Jimbo, Mira, and Ueno. If you look in there, there's this wild monogamy relation which occurs. So if you then read the group valued moment map paper, it's just like, crying out to you that you need to prove that this monogamy relation is a group valued moment map relation as well. Is there a quasi-Hamiltonian structure on these spaces? So here's the Stokes data and the formal monogamy, and these connection matrices, these C's, which were in the group G earlier on. So this is just an explicit writing out of the monogamy around the G boundary that we had before. Is there a quasi-Hamiltonian 2 form on these such that this is a group valued moment map? That was the question which came up in like 1998 or so, and was proved in this paper in 2002. So you can define these fission spaces, and this is a quasi-Hamiltonian T to the M cross G space. So the G part of the moment map is the monogamy relation which occurred in this 1981 paper. And really, as they say, this goes back to Birkhoff's paper 1913. He has an earlier paper in 1909, so perhaps it's in there too. But It's definitely in the 1913 paper, and it's spelled out very clearly in this paper of Jimbo Biryani. And so you can phrase it as this, the G fusion of these fission spaces gluing fusing the G boundaries like in this picture, and you've still got the torus actions or the H actions at the outer boundary here to do with the formal monogamy. So the statement here would be, in this generic case, that the reductions with fixing a conjugacy class in the torus is just fixing a point. And so these reductions with fixed formal monogamy in T are symplectic. And there was an analytic proof of this earlier on, this irregularity bot picture. And then we got to this algebraic quasi-Hamiltonian picture. And there was also this other analytic picture, a third perspective in this paper with Bickard, which upgraded the hyperkähler picture. So we had these three sort of different perspectives in 2002 or so, at least in the case where the formal monogamy was in this abelian group. So the general story is similar, and you have this twisted picture. Let me just state the picture. So basically the Stokes groups can be much more complicated, and you don't have to have an even number of them. For instance, for the area equation, you would just have 3. You still have these connection matrices, but in general, they may not be in G, but in a twisted version of it. But this is all explained in this paper with Daisuke from 2015. You would look at torsors for a local system of groups, and then you have this sort of grading at the boundary, which may be twisted. And you have to understand what you mean by grading in the G case as well. And there's a nice way to do that in terms of an infinite dimensional torus. So at the end of the day, you get these twisted Stokes representations, which again can be got by fusing some fission spaces and some copies of this internally fused double. And so you get lots of new algebraic Poisson varieties like this. And so the story is as before. You can just do the straight quotient by the framing group. So here you have a copy of 8 at each of the marked points on the outer boundary after you've reduced the structure group, and this space of Stokes representations will be a Poisson variety with symplectic leaves got by fixing these twisted conjugacy classes around the boundary. Okay, so there's a sequence of papers which did that. The general untwisted case was here, and this is extended to the twisted case in 2015. So the picture is that we get this large class of Poisson varieties from gauge theory in this way. Let me just talk about the basic examples, which somehow provided quite a lot of the motivation. So when I did this, I was sort of trying to understand the braiding in Dubrovin's paper and what is the general story which generalizes that, what is the braiding in general? And it turns out that the basic examples explain, the quasi-classical picture under the quantum group. So the simplest case would just have these 2 tangential punches like GA1T with a full reduction to like a full grading. So it breaks it into 1-dimensional pieces. And here this moduli space is just T cross U plus cross U minus with a Hamiltonian action or quasi-Hamiltonian action of T, but it actually is Poisson and not quasi-Poisson because T is abelian. So it turns out that this space is well known. So Drinfeld and Semenov-Shansky and others understood that the Drinfeld-Jimbo quantum group has an integral structure such that you can put Q equals to 1 and it becomes the dual Poisson-Lie group, which has a space is isomorphic to T cross U plus cross U minus. And the statement is that this Poisson structure that we get from the gauge theory perspective is isomorphic to this Poisson structure, which comes from the quasi-classical version of the quantum group. So you get this isomorphism that can be phrased like this, that the quantum group Poisson structure is indeed coming from modular spaces of connections on curves. So we can phrase this slightly differently. I mean, we have this large class of Poisson varieties which occur either as M star or as MB in this story of sort of, what are the Poisson structures in 2-dimensional gauge theory, and you can see that this space G star occurs in there. So we can say that the Drinfeld-Jimbo quantum group is modular, as in it does occur in amongst the modular, or the quasi-classical version of it occurs amongst the moduli spaces which occur from connections on curves from 2D gauge theories. So I'll try to use modular in this way, not as modular. Well, it's maybe different than the modular that Wiles and others speak about, but nonetheless, it is a moduli space of connections on curves. The next example would just be to do the same thing, but allow a non-abelian formal monogamy. So I've replaced the torus by H here, so I have this block diagonal group. And if you quotient by G cross H, you get an algebraic Poisson variety with symplectic leaves, as always, got by fixing the conjugacy classes of monogamy around the 2 boundaries. So you fix a class in H and in G like this. And so this is some Poisson variety. And it turns out that there's a Fourier Laplace transformation that identifies all of the spaces which occur in this case on the nose exactly with the class of spaces that occur in the tame case in genus 0. So if I look at a genus 0 curve and just have an arbitrary number of punches and choose an arbitrary conjugacy class at those, and we construct it properly with the stable points, then on the nose that is isomorphic to the spaces which occur in this case just with one irregular pole, in fact a pole of order 2 with an untwisted normal form, here. And so that's really what the Fourier Laplace transformation in the simple case of the tame story gives you. The Laplace transformation is a moduli space which occurs like this. So this really goes back to Fourier Laplace, and in this generality it was written down in an appendix of Malgrange's book. One can prove that the simplexical Poisson structures match up as well. I was trying to develop this multiplicative quiver picture. So if we know certain examples where the space M star is a quiver variety, it's natural to think of the multiplicative side as the multiplicative quiver varieties. So in general, the usual multiplicative quiver varieties don't give the right spaces. So there's some new theory of multiplicative quivers which occur, which give you these Betti spaces. But it turns out in this example, the quiver is a star. And so this is like two ways to read a star shape or a star-shaped multiplicative quiver, either to give the moduli space here or the tame picture, which has got lots more poles. So basically the number of points of this grading set I is the number of simple poles which occur. And there's a story about how to read off the ranks and everything. This was upgraded in a paper with Sabo, which proves that this is actually a hyperkähler isometry as well. Maybe he only proves the case with a toral boundary, but I think it's true in general. So you start to get this abstract picture where you want to think of it like a Lie group, and so you want to make the definition of what is a global thing like a Lie group. You want to have an abstract definition and then separate representations of it. So here we have some abstract hyperkähler space with all of this structure, and there are two different representations of it. Either as this irregular representation here, or as the tame picture having simple poles. And it turns out that all of these moduli spaces in genus 0 have an infinite number of different representations or realizations. We would like to understand this sort of nonlinear representation theory which occurs. Okay, so if people know this, this symmetric How duality picture, so that's kind of the M star version of the duality which occurs here. So here we're really looking at some type of multiplicative symmetric How dual picture, which is a way of thinking of what this Laplace transformation on Betti data does. Okay, are there any questions? I want to switch to the quivers now. Is this kind of clear, or okay, so I think there's probably lots of experts on quiver varieties here, so I can probably do this section quite quickly. So basically I want to explain how I got into this sort of, or how I fell into this trap of wanting to describe these spaces in terms of quivers. And it was kind of an accident. I was invited by John Harned to give a talk at a conference in honor of John Mackay in 2006 or so. And I thought I would explain the link between, sort of Mackay's work and Harnad's work. I thought I would be clever and explain the link between their work. So Harnad has lots of work on, isomonogamy and these spaces M star in certain examples. And if you understand the quiver picture, you can link that to the correspondence of Mackay. So it's as if it's the link between the Platonic solids and the Pauli equations, which are these simplest examples of these moduli spaces of complex dimension 2. But in particular, I wanted to answer this question of Sakai, who was asking about a lax pair for the additive Pauli difference equation for type E6, 7, and 8. And if you understand the star-shaped quiver picture, it's easy to see what to do. So I wrote a paper in there. And then I sort of carelessly pointed out that this works more generally. It works in the irregular case as well. So that was exercise 3. And I've basically spent, my spare time in the past, times since then, trying to understand what this means in general beyond these simple examples. So let me tell the story that people here probably know, so I'll be quite quickly. So you have these rotation groups, the tetrahedron, octahedron, and icosahedral group, and these have these binary groups as well. And then you can look at this corresponding singularity quotienting by these groups. And then you can resolve these, and then you can deform them. So these have deformations, as I mentioned, 6, 7, and 8. And there's a natural action of the finite Weil group of type E6, 7, and 8 on these. And Kronheimer proved in 1989 that the smooth fibers have complete hypercalometrics. And you can construct these as a hypercalar quotient built out of the affine-Dinkin graph. And these were later generalized to become the Nakajima quiver varieties. So if you don't know the story, let me just sketch the complex symplexic approach, or the holomorphic symplexic approach. So for instance, for E6, you would draw the affine-Dinkin graph like this. You would take the minimal imaginary root, or the dimensions of the corresponding representation of the finite group, and you would put a vector space of that dimension at each node, and you would look at the map. So I would say a representation of a graph is a representation of the doubled quiver. So you have these maps in both directions along each edges, and you construct this large sort of graded group. So this is like the graded automorphisms of the graded vector to space. So V has a natural symplectic structure, and this graded automorphism acts in a Hamiltonian way. So you can do the additive symplectic reduction at some scalar value of the moment map, and you get some space. So this is the Nakajima quiver variety, and the dimension is 2 minus sort of d squared. So in particular, if you have an affine graph, you have this null root, so you can get d squared equal to 0. You get space of complex dimension 2. Hypercalar 4 manifolds. These are the Kronheimer ALE spaces, generalizing Gibbons-Hawking and Iguchi-Hansen and people. In these cases, you can do more because these are modular. They fit into this story of connections on curves. Here it's a tame picture, so it's a modular space of Fuchsian systems M star. So this can be thought of in various ways. Basically, you can do the quotient by the group, the component of the group that will last, and so you get these 3 legs, and it's known that these legs give you coadjoint orbits or adjoint orbits in GL3C. And so the space really is a diagonal symplectic quotient of the product of these 3 orbits, and they become the residues at 3 poles of a Fuchsian system. So these symplectic moduli spaces of connections in the tame case are isomorphic to quiver varieties. This was worked out in general by Nakajima and Crawley-Bouvier. I guess Kraft and Procesi and Nakajima had looked at the story on the legs, and Crawley-Bouvier put it together to get this global picture and related it to the tame Deligne-Simpson problem. So in particular, in these cases, we can take the multiplicative picture that we have a group-like space as well. Here it's just the character variety, the space of representation of the fundamental group. Now for an arbitrary quiver, we don't really know what the right multiplicative space are, but there are some quiver varieties that we can identify with these spaces M star, and in those cases we know what the spaces are. I mean, I forgot to mention early on, there's this sort of game of spotting what the spaces M star are, and then you put in a Poisson variety and it spits out a multiplicative space. So for instance, there's a way you can put in the dual of the Lie algebra as a Poisson variety, and it spits out this dual Poisson Lie group. And there's a different case having 2 poles order 2, where you can put in a framed moduli space being the cotangent bundle of the group, and this will spit out the so-called Lou-Weinstein symplectic double groupoid. And so there's a very clean, like, gauge theory way, if you understand how to read the moduli spaces, to get lots of like well-known spaces that people in algebraic Lie theory have looked at. This Lou-Weinstein example was in this Duke paper from 2007. Okay, so it becomes more interesting if you realize that there's another star-shaped affine-Dinkin graph. You can look at affine D4 as well, the 4th star-shaped affine-Dinkin graph. And this is more interesting. It has 4 legs, not just 3. So you have the moduli of those 4 points on the sphere as well, not just, so the others only had 3 legs, and so you had no moduli. The moduli space of 3 tuples of points on the sphere is a point. Whereas now we've got 4 tuples, so we've got the cross ratio as well. And so there's like an other deformation parameter. There's the constants that we had before, which essentially always match up with the exponents of formal monogamy. But you also get these modular parameters, which become the time in the corresponding Painlevé equation. So we can vary that. So you get this big picture, which is somehow well known to the isomonogamy people, and goes back to Richard Fuchs in this tame picture for Painlevé 6, that you look at these families over the space of time. So the base space is now the moduli of 4 tuples of points. And you can look at Riemann-Hilbert in families. You've got these M stars as the fibers here and MBs here. And on the Betty's side, you can identify the nearby fibers by saying that they have the same representation of the fundamental group. This is the Betty version of the isomonogamy connection. And you can pull that back and get an interesting algebraic differential equation here, the Panlevet 6 equation that looks like this. And you can describe the Betty spaces. This goes back to Volt and was rediscovered by Frick and Klein. So you get these 4 parameters, the constants occur here. And the time over here really is the coordinates on this 4-puncher sphere, or perhaps a cover of that. Okay, so you get this really rich geometric picture. This is how, Panlevet equations are related to these, quivers. So this is the case for Panlevet 6. And in the world of Panlevet 6, Okamoto had already discovered the full affine Weyl group acting on the space of the constants. Whereas Kronheimer was just looking at the finite Weyl group, Okamoto is really looking at the full group-like space, and then you get the affine Weyl group, not just the finite group. And then you scratch your head for a bit and you realize that this is the Panlevet 6 equation, and there are 5 others as well. And so you wonder what's happening there. So there's a review paper by Okamoto in 1992, the Panlevet equations and the Dynkin diagrams. He has a nice table in there. So he lists the Panlevet equations, the number of constants which occur. So 4 for Panlevet 6 is this c to the 4, and the relation to affine D4. And he says, well, for Panlevet 1 to 5, you get the trivial group, your affine A1, affine B2, affine A2, affine A3. And we know that there is a well-developed theory of quiver varieties for A1, A2, and A3. So we think, well, we can do something there. And we're very puzzled about B2 here. So let me rewrite this question like this. So this exercise says that this works for Panlevet 2, 4, and 5 as well. So the case is A1, A2, and A3. So perhaps you have the simplest affine Dynkin graphs which occur. So the quiver variety does match up with the affine Dynkin graph that Okamoto had. So you can sort of redraw this table and put in some question marks where you are puzzled. So we get these affine graphs like this. For 2, 4, and 5, we get affine A1, 2, and 3. It's affine D4 that we had before. And these all have these special solutions that Okamoto talks about. And this basically is got by sort of de-affinizing or removing the extending node. In the case of affine D4, he says the special solution is the Gauss 2F1, and that is indeed the non-affine graph which occurs here. So you would expect that to happen also in the other cases as well. And it's puzzling what's happening for these other cases here. So there are various questions that can be asked. You can say, well, what are the higher dimensional modular quiver varieties lying over these examples here? And you can ask what's happening for these other ones like Panlevet 1 and Panlevet 3. Those are the questions I want to focus on in the rest of this talk. There are other questions you can ask which are extremely interesting as well. What are the deeper analogs of this space of modular parameters, the times, generalizing N04? This leads to this theory of sort of moduli of Weyl-Riemann surfaces, that you really want to add the irregular times to the definition of the moduli of the curve. This philosophy, I mean, I talk about this quite a lot at the moment, but I don't necessarily explain the philosophy. The philosophy is that Simpson has defined the nonabelian Gauss-Manin connections in general for an arbitrary projective variety. In the case of a punctured curve, you get these, this Betty vibration with a flat connection in the Panlevet 6 case. And so you want to think of these Panlevet 1 to 5 in the same way, but as if you need to generalize the definition of a Riemann surface. And so that's what leads to these wild Riemann surfaces. The Panlevet equations 1 to 5 are the non-abelian Gauss-Manin connections for the wild Riemann surface. So that's a nice way to think about what's happening. And it was sort of a remark in this 2001 paper in Advances in Math, but it's underlies this general philosophy. You can ask, what are the deeper analogs of this? And this is the irregular isomonogamy connections. Okay, so now let me get to the answers to the questions if I have time. Let me first give a precise definition. There are some references for this, but it's basically the models which are in this paper with Bickard, and there's some paper which gives various expositions of this, maybe trying to phrase it in a slightly cleaner or more intrinsic way. So the picture is you would have a compact surface with some marked points. You would look at holomorphic vector bundles, parabolic filtrations at the marked points, and look at meromorphic connections with arbitrary order poles. So there's really nothing that's stopping you looking at meromorphic connections, apart from the fact that lots of geometers are not so familiar with the structure at the irregular poles. But nonetheless, it is known to various degrees of generality by various different people. It's just that lots of people are experts on different things. And you put in these conditions to get these sort of good or very good connections, such that we have moduli spaces, that we have a Betty picture of the right dimension. So you say that you have local trivializations which split the parabolic filtrations, and you can diagonalize the irregular part. So you get this Q here, which is diagonal. This is the irregular part, and then you have a logarithmic connection, so poles order 1, like this. And so you put in this condition, and this has to be compatible with a parabolic filtration in a particular way. And then you say, this is very good, and it's good if there's some local cyclic pullback, which reduces to this very good case. And that's it. Those are the ones that we sort of know what to do with, and we have an extension of all of these pictures. So you can look at the Dirac moduli spaces with these fixed irregular type, and the sort of basically the formal monogamy. But then you can do the same on the Higgs side by looking at very good Higgs bundles as well. So there is a definition that can be done there. Let me not dwell too much. Let me look at examples. So I just choose a curve with marked points and a irregular type. And we fix the eigenvalues or the orbit of the residues, the formal residues, after you've put them in these like block diagonal form. So the main examples we want to look at to get this quiver picture is just the case of one pole with an untwisted irregular type. So Q is just some diagonal matrix of meromorphic functions. And then we look at the space M star. And the theorem is that in all of these cases, you do get something which is isomorphic to a quiver variety. So this was proved in general by Hiroi and Yamakawa. And so you get a special class of quivers or graphs which are modular, that do occur in this story of connections, of space of connections on curves. So we can call them the supernova graphs. It's possible to write down explicitly what the quiver is or the graph is in terms of the matrix entries of this irregular type. You can look at the degree of the differences like this. And so that gives you a nice class of quivers which occur, for which we have this whole sort of wild nonabelian Hodge Dorian. So these are the graphs we want to use to try to classify these spaces, e.g. the affine D4 with dimension vector like 1, 1, 1, 2 would give this panel of A6 picture, all of the different structures which occur there. And there are lots of others. For instance, the tetrahedral graph, the square occurs, all of the complete graphs occur. So these are the graphs which generalize the square and the triangle and affine D4, which occur in the panel of A case of dimension 4. And so there's sort of special class of graphs in arbitrary dimension, but we can't take an arbitrary graph. So the idea of the proof is basically to look at the moduli spaces which occur. So there's a Birkhoff orbit that occurs at the infinite point, and you can prove that this Birkhoff orbit is isomorphic to the vector space which occurs in the Nakajima quiver picture. So the main thing that Hiroi and Yamakawa proves is that there's an isomorphism, an algebraic isomorphism as Hamiltonian H spaces between this Birkhoff orbit OB. So the Birkhoff subgroup is where the constant term is 1. The moduli spaces with just the one pole can be described as an H reduction of this Birkhoff orbit. I knew this had symplectic global Darboux coordinates for a long time, but I hadn't really specialized in GLN. So it took a while to realize that you should think of OB as the large symplectic vector space. And once you do that, you see that there is this special class of spaces which are isomorphic to quiver varieties like this. I mean, a lot of the integrable systems that occur, like the finite gap solutions of AKNSD are in this situation where you just have one pole of arbitrary order. I think Dubrovin went back and revisited this situation in a paper in 2018, but this was understood somehow back in the 60s or so. So for instance, the simplest case is this panel of A2, the affine A1 picture, where you have your irregular type has got these X cubes. The nodes correspond to the two pieces here, and you get two edges between those. This is the lax pair for panel of A2. And so the additive space is this Gucci-Hansen space, but we have this full multiplicative space, the sort of the new hypercalometric, which occurs in this sort of global Lie theory picture, in this paper with Bickard. It's a multiplicative version of the cotangent bundle of P1. The explicit algebraic equation occurs in a Flaschke and Newell paper from 1980 or so. You can actually write down what the Betti space is explicitly. And I went back and wrote a survey paper on this in 2015 or so that talks about these sort of, actually the whole class. So the cotangent bundle to P1 here was generalized in a paper of Calabi, which gives the cotangent bundle of CPN. And so all of those occur in this story. And so we get these multiplicative Calabi spaces. So I have a paper which sort of talks about this story, the Calabi examples and the multiplicative version. And that has a nice link with these Euler continuum polynomials as well. Okay, so the question 2, the answer is that there's a uniform way to define a diagram. So for an arbitrary connection with just one irregular singularity on P1. So the point is that we now understand what happens in the twisted case as well, where your grading has these twists. And in all of the cases, the dimension, as in the quiver picture, is always 2 minus d squared, where this is the symmetrized Cartan matrix that comes from the diagram which occurs. And the point is that in general, you get these negative edges or loops as well. So you get sort of things on the diagonal, which may have like a 4. If I look at this panel of A3 picture, the diagram which occurs is like this. And so, we knew that one can reduce to the case with just one irregular singularity with some type of sequence of Laplace transformations. So I thought if you have a good student, you should be able to ask them, to do this. And so this was done by Dussault in 2021. And so we can just look at the case for arbitrary poles on P1, and there is a precise definition of the diagram of that space. And basically he proves that all of the choices that you might make to reduce to the case with just one irregular pole make no difference, and you do get a well-defined diagram in general. So you get these negative loops. So if you normalize this, if you multiply through by like 1/2, 1, then you get the transpose of affine B2. So that kind of explains why the Weyl group of this matches the Weyl group that Okamoto has. It's really like the Langland's dual of affine B2, which is occurring. And I sort of like to call it affine D2 because that matches up with the physics perspective and the fact that the additive space is the D2 ALF space, where it is naturally diffeomorphic to the the D2 ALF space, which is involving the cotangent bundle of SL2C, which occurs in this case with 2 poles order 2. And indeed, these special equations, these Bessel-Clifford solutions are got by removing a node. And so that picture works nicely. And the strategy was to just repeat the additive picture in this multiplicative picture. Now we have this nice quasi-Hamiltonian picture. We can just repeat all of the additive spaces in the multiplicative spaces. So there's this extended orbit occurs in the additive picture, which has a G cross H action. And this is the additive version of the fission space, having the G and H at the boundaries. There's also the reduced fission space, this space B. If you just cap off the G end of it, you just have an H action. So that's the multiplicative version of these Birkhoff orbits, OB. So this really gives you the sort of the analog of the large symplectic vector space in the multiplicative quiver picture, if you accept that the standard multiplicative quiver picture is not right in general. This is really what the Stokes data tells us. And then you have these deeper conjugacy classes, which are the reductions of these once you fix the formal monogamy. So this C is not a conjugacy class of the group of K jets or whatever. It's just something which is built out of the Stokes data, but it does play the role of the deeper orbits which occurred before. So you have a G action here, and this becomes the quasi-Hamiltonian G action, which is there. So I wanted to just sketch what the general definition is, and this requires a lot of sort of discussion of the formal structure of connections. This is known, but maybe not well known. So the basic idea is that graded local systems occur naturally at the poles. There's a theorem of Deligne, which is really a restatement of lots of work before, that says the connections on the formal punctured disk are equivalent to the I-graded local system. So you look at the circle of the directions. The fact is that there's a covering, some huge infinite collection of circles, such that an I-graded local system is the same thing, or there's an equivalence of categories between these and the connections on the formal punctured disk. And this gives all of the graded local systems that we want to have, at least in the GLM picture. And then in this paper with Daisuke, we understood how to generalize the definition of graded local system for other groups as well. And so we have this I-graded G local systems, and eventually I-graded twisted G local systems as well. So this I is built out of the exponential factors. You just realize that there's a nice intrinsic way to do it. And so these exponential factors which occur in differential equations can be viewed as circles, and you get I to be the collection of the circles. So to get a moduli space, you want to fix the irregular class of the circles and the multiplicities. And to get a symplectic leaf, you fix the conjugacy class in each of these. So C is a class in GLNCI. And then there's a formula for what the definition is. There's certain numbers that can be attached. There's these points of maximal decay, the poms or apples, which are finite subsets of each circles where each has maximal decay. There's a number like the number of wiggles that each circle has, the number of apples on it, and the degree of the cover. And then if you fix this irregular class, you can define the diagram just by extrapolating what people did before, what the additive definition became over here. And so you do get a definition of a Cartan matrix, and then you can glue on the legs as before from the classes on each of the circles. So let me just end, if I can take a minute extra to just go through a few basic examples. So for instance, for Panleve 2, we had this affine A1 picture before. We can look at the Stokes diagram, which gives the growth and decay of the exponential factors. We can draw this, and then Stokes would have these sort of, gluing. So these directions, to define the Stokes root, you look at the biggest differences. So this arrow is like the matrix entry in the unipotent matrices, which we had over here. So you draw what this is, and so the maps, the matrix entries become maps here. So this really is a quiver, that we have the formal monogamy on these two circles there, the graded local system. And then the maps along the arrows really give you a quiver here. And you can draw this, you can slide it around. It does look like this. And then there's a monogamy relation which occurs. There's this multiplicative symplectic reduction. So you're subtracting off the monogamy relation, which is a 2x2 matrix equation. You subtract off this, and again, you get affine A1. So that tells you how to read off the quiver or the graph from the Stokes data. And once you understand that, you can do it in the arbitrary twisted case as well. So for instance, for the area equation, if you look at Stokes's paper, there's the Stokes diagram for the area equation is actually in Stokes's paper. So I think Kontsevich was giving lots of talks with these pictures in, and I sort of point out this is actually in Stokes's paper. And so it's sort of, great minds think alike somehow. So if you do the same thing here, you just get a point. So this is like A1. You get these three entries of the Stokes matrix. You get this one circle that goes around twice. This is this, and then you subtract off the relations which occur, you just get a point. So this is rigid. The moduli space is a point. The next case is this Panleve 1 picture. So I draw this slightly differently with this sort of fission surface. So it's just as before, but now we get a 5 rather than a 3. So you get 5 matrix entries. So you get a quiver at the top, which is like the double of this. And then the relations are as we had before, but then you get affine A0. So this explains the trivial affine Weil group that occurs in Okamoto's case for Panleve 1. So at the end of the day, you can complete this table. This is just the, the moduli space of complex dimension 2, the H3 surfaces, if you will. They're sort of non-compact analogs of K3 surfaces in the case where you have a non-trivial modular parameters. So we ignore the E's, the E6, 7, and 8. You get this picture, and you can remove a node to get this. And you get, if you look at the Kummer equation, which gives the special solutions for Panleve 5, indeed, the diagram we get is the right one, which is got by taking off a node there, and the same for the Weber equation. Okay, and the next sort of simplest class of examples are like the Hilbert schemes of these, or they should be the Hilbert scheme. The fact is we can take the nth multiple of the dimension vector which occur here and add on this one which is at the foot. So in the quiver picture, this is well known to be related to the Hilbert scheme. So expect that to be true in the full like multiplicative picture as well. And this was proved by Groschnig in the tame case, but his methods don't work in general. But nonetheless, I think it's true. And we may even know a proof of it, but I don't think it's been written down or checked carefully. But nonetheless, we do get these sort of higher Pan-Lavie spaces as well. But of course, there's lots of other graphs which occur. I will stop there. Sorry for going slightly over time.
Thank you very much. So, any questions from the offline audience? Anton?
Philip, maybe I kind of got a bit confused. So at some point you mentioned hyperkähler metrics, and then they somewhat disappeared from the discussion. Could you say in general, so in which case one gets hyperkähler metrics, or so when is it known, when it is not known, just to orient ourselves?
Sure, let me go back to so there's this space M here, and then there's a question of what you mean by known. So in the paper with Bickard, we look at the general case for GLN, which is untwisted at the boundary. And then we spoke to Sabat, and then there was some correspondence with Witten, and it became clear in 2007, and I think it was clear to Sabat before, that there is this trick with passing to these cyclic covers, and the same argument works verbatim. And so in all of the good cases for GLN, there is a hyperkähler metric there, and it's complete if there is no nilpotent part in the associated gradient of the formal monogamy. You have this parabolic filtration, and there are no strictly semi-stable points in the modular space. So we make that statement carefully in the untwisted case, but the same thing works in the twisted case as well. I imagine there's statements that will work for other groups as well, but there's like an ongoing discussion about the right definition of sort of stability for parahoric bundles and meromorphic connections on there. Basically, there's a large number of like sort of pure mathematicians who have kind of not understood the importance to the theory of integrable systems of irregular poles. That I can take very basic examples that were looked at by sort of Dubrovin and Krzywa, going back to the French mathematicians like Garnier and Pan-Lavie, where they have a pole of order 2 or a pole of order 3. You can look at Cherednik's work on Baker functions and Krzywa's work as well, and there they have the spectral curve, and the the times which occur in the Baker function is the irregular type which is there. So the definition of an irregular type, which I have, if you specialize to the rank 1 case, and then you read Cherednik's book, you will see that that definition is already there when he does Baker functions properly. So, yeah, I think I've answered the question and said more than I need to, but that's the story. Is that clear?
Okay, thank you.
Questions?
Yeah,
Okay, so the last thing is speaker again.